Let's think about thermistors next. Thermistors are basically thermally sensitive resistors. So these are devices that change its resistance depending on the temperature that the thermistor is put into. Now, thermistors are made up of semiconductors and they have highly nonlinear characteristics, as we would see in just a moment. You have got, in general, we have two types of thermistors: negative temperature coefficient thermistors. These are the most predominant of all thermistors, and we'll be looking at these kinds of thermistors in a moment. These thermistors, the resistance of these thermistors decreases as the temperature increases. Okay. Then we have got positive temperature coefficient thermistors. These are thermistors whose temperature actually increases, whose resistance increases as temperature increases. Okay. So let's look at the characteristics of negative temperature coefficient thermistors. And you can see that here, as temperature is on the x-axis, and as temperature goes up, the resistance is actually going down. So these are negative temperature coefficient thermistors. And what we are doing is we are looking at zero power characteristics. Now, what does that mean? Now, whenever you are using a resistive sensor to measure temperature, there is this issue, right? So, how are you going to measure temperature? How are you going to measure a resistance? And how are you going to convert the resistance into a voltage? The only way to do it is to pass a current through that resistance and then measure the voltage across the resistance. Okay. Now, if we have a thermistor that is changing its resistance based on temperature, we pass a current through the thermistor so that we can measure the voltage across it and find out what the temperature is. But just the fact of passing the current through the thermistor increases the temperature of the thermistor, right? Why? Because there is a power dissipation in the resistor. What's the power dissipation in the resistor when a current I is flowing through it? It's I squared times R. I hope you remember that from cardiac engineering when you were introduced to resistors. So the power dissipated in a resistor is current square times R. So I square R. So that's the power dissipation, and this power dissipation is going to increase the temperature of the resistor. Now, if it is a thermistor that is measuring the temperature of the environment, then you have power dissipation because of the current that is increasing the temperature of the thermistor and the environment that is influencing the temperature of the thermistor. Okay. If you keep your current very, very low, you can almost ignore the power dissipation and its contribution to the temperature of the thermistor. And that's when we are taking this characteristic. And that's why we call it zero power characteristic. We cannot really have zero power, but we can have very, very low power so that the temperature of the thermistor is almost entirely determined by its environment and not by the power dissipation due to the current flowing through it. Okay. Okay, so let's look at this characteristic in a little bit more detail. As I said, they are highly nonlinear and the resistance decreases as the temperature increases. You could compare this with this characteristic in green, which is the characteristic for a resistance temperature device. You would have a similar characteristic for a positive temperature coefficient thermistor as well. And you can see that here the resistance is increasing as the temperature increases. And this would be the normal characteristic for any resistor, right? As the temperature increases, you expect the resistance of the resistor to increase. But that's not the case for thermistors. Now you could model this characteristic by an equation like this. So this is an approximation to this. There are two basic quantities that are important at this point. One is R naught and another is B. R naught is the resistance at the reference temperature T naught. And usually we take this reference temperature to be 25 degrees Celsius. And that's the reason why each of these curves is marked by an R25 value. So this is R25 equal to 100, 1 kilo ohm and 5 kilo ohm. What that means is that the temperature of the thermistor at 25 degrees Celsius is 5 kilo ohms. Okay, so the blue trace uh, is the characteristic of a thermistor whose resistance at 25 degrees Celsius is 5 kilo ohms. This thermistor has an R25 of 1 kilo ohms and this thermistor has an R25 of 100 ohms. Okay, so that's the first characteristic, the first parameter to describe a thermistor. The second parameter is this B. This B is called the characteristic temperature of the material, and uh, this is another parameter that is used to describe thermistors. In this equation, the temperatures are given in Kelvin. Okay, so just be careful there. Sometimes what we do is inadvertently we put our temperature in degrees Celsius and we get all kinds of results that don't match with the theory. Okay, so let's take a look at the next characteristic. Now, this is the voltage versus current characteristic of the thermistor. As we already discussed, the temperature of the thermistor is influenced by two factors. One is the environment, or the temperature of the thing that we are trying to measure. So let's say you're trying to measure the temperature of the room. So that is the environment for the thermistor. Or you're trying to measure the temperature of a water bath. So that the water in the bath is the environment for the thermistor. The thermistor is put inside that. So that influences the temperature of the thermistor. So that's good. We want that, right? We want to measure that influence. But there's a second element to the change in temperature in the thermistor, and that is the power dissipation because of the current that is flowing through the thermistor. We discussed that a little while back. Uh, and basically, what we said was that because the thermistor is a resistor, and to measure the change in resistance, we need a current flowing through that resistance. That current would cause a power dissipation in the resistor, or in the thermistor in our case, and would increase its temperature. So there are these two competing aspects. The voltage current characteristic measures the second of these influences. So assume that the temperature of the environment is kept at a constant temperature. What happens when you increase the current through the thermistor? Okay, so here's what happens. So initially, what happens is you just are on a straight line. Let's say you take a thermistor whose resistance is 100 kilo ohms and at a particular temperature, and you don't change the temperature, and you start giving it a small amount of current. The voltage would just be the current times 100 kilo ohms. Okay, and that is maintained till point A. So basically, till point A, whatever power is being dissipated by the current in the thermistor is too low to change uh, in any appreciable way the temperature of the thermistor. But as you keep increasing the current, as you can imagine, what would happen is the thermistor starts to get hot. And as the thermistor starts to get hot, what is going to happen? What is going to happen to the resistance of the thermistor? It's going to go down, right? Remember the previous curves that we saw? As temperature increases, the resistance of the thermistor goes down. So the resistance of the thermistor goes down, and therefore this curve actually starts bending from this 100 kilo ohms curve and starts to move towards a lower resistance. Okay, so it starts to move towards a lower resistance, and we reach a point B, after which, even though we increase the current, as you increase the current, what do you expect? you expect the voltage to also increase, right? Because I times R is V. But now what happens is the increase in current increases the temperature of your thermistor so much that its resistance goes down, and therefore the voltage then doesn't go up but it starts going down. Okay. So B is the kind of the peak voltage that you can get. And as you keep going down this characteristic, at a certain point, you will start having so much power dissipation in the thermistor that it's going to burn. And that's the point C. Okay. So, and you can see that here, the lines that are drawn like this are the power dissipation lines. And as you are moving like this, you're having higher and higher power dissipation. And as you have more and more power dissipation, there would be a time that would come when the thermistor will not be able to handle that power dissipation and it will just burn off. Okay, so this place, the phenomenon that's happening in this place is called roll off. It's called a runaway. Sorry, it's called the runaway phenomenon. And here, what is happening is, um, if okay, so if you have a voltage source across a thermistor, okay, um, so the resistance of the temperature is R, so the current flowing through the thermistor is V over R. Now, because the current increases the temperature of the thermistor, the resistance of the thermistor goes down. So V over R, the current increases. Okay, if the current increases, more power is dissipated in the thermistor, and therefore the resistance of the thermistor goes further down. And if it goes further down, what is going to happen? The current through the thermistor more current starts to flow through the thermistor. That results in the resistance going down a little bit more, and more current flows through it, which results in the resistance still going to a lower value, and the current increases more. And so this vicious cycle just keeps happening till the thermistor burns off. And that's why this area is called the runaway. Of course, as you can imagine, all this is also determined by how much heat is taken away by the environment. So if you put the same thermistor in water, you might get a curve like this, while in air, the curve was like this. So one of the things that you have to be careful with thermistors when you're using thermistors is that you don't want it to go into runaway. And one of the ways to control it not going into runaway is, instead of voltage sources, we use current sources to control the current in the thermistor. We make sure that the current through a thermistor cannot exceed beyond a certain value, and that would kind of prevent runaway.